In this video, we are going to solve logarithmic equations. And there are kind of two different types. In the first type, first bullet point, we can get both sides of the equation in terms of one logarithm with the same base on each side. And when that happens, just set the argument on the left equal to the argument on the right and solve. Sometimes, though, in the second bullet point, we have a logarithm on one side and a value on the other side. When that happens, rearrange the logarithmic equation to its equivalent exponential equation. As you know, if log base b of a equals c, then b to the c equals a. Do that rearranging, and then you'll see that we can solve for the variable. So here's a question that's relatively straightforward. We're going to use our power rule of logarithms, which states that a coefficient in front can be raised and made to be the exponent, as we see here. So we're going to, in that way, get the left-hand side in terms of log base 7 and the right-hand side in terms of log base 7. So bringing that 8 up, making it an exponent on 2, we get 2 to the 8 as our argument on the right-hand side. 2 to the 8 equals 256. So we have log base 7 of x equaling log base 7 of 256. Since we have the same log, same base on both sides, we can just focus on the arguments, and we can say, therefore, x is equal to 256. Now, let's look at this equation. This one's a little bit more straightforward. We have a log base 5 on the left and a log base 5 on the right. All we have to do now is just set the argument on the left equal to the argument on the right, as it says on this slide. So we can just simply say 3x plus 1 is equal to 37. Solve that out, and we get x equal 12. That's our final answer. Now, what if we have here log base 4 of 2x plus 1 is equal to 3? Well, this is the different type of question. This is like the second bullet point. We're not likely going to get this in terms of a log base 4 on each side, but instead what most people will do is they'll say, rearrange this as an exponential equation. The base of 4 raised to the exponent of 3 is equal to 2x plus 1. Once you do that, it's pretty easy to solve. Okay, so like it says in red here, we know from the definition of a logarithm how to rearrange to get the exponential. So ultimately what we get is 4 to the exponent 3 equaling 2x plus 1. That means 64 equals 2x plus 1, and ultimately x is equal to 63 over 2. Now in this question, we've got a couple of logarithms on the left-hand side. Well, let's use the power law of logarithms to take this 1/2 coefficient and put it up as an exponent on 16. And then after we do that, we're going to be in a position to use the power law of logarithms and multiply those two arguments. So what we do, we take this, as we said earlier, we take this 1/2, bring it up here, and that gives us what you see here, 16 to the 1/2. Now we know that 16 to the 1/2 is equal to 4. So in this line here, we've got log base 6 of 3x plus 2 plus log base 6 of 4 equal to 3. Now, we know that if we have the same log, we're adding two logarithms and it's the same base. When that happens, what we can do is make one single logarithm where we're multiplying those two arguments. And we show that. And so what we have is log base 6 of 3x plus 2 times 4 equal to 3. Well, we know that 3x plus 2 quantity times 4 is the same as 12x plus 8. That's just using the distribution property. So now that we have that, what we can say is that the base of 6 raised to the exponent of 3 is equal to 12x plus 8. And we're going to be able to solve from there. So that's what we're going to do here. We have log base 6 of 12x plus 8 equal to 3. 6 to the exponent 3 therefore equals 12x plus 8. So 216 equals 12x plus 8, meaning 208 equals 12x. And ultimately, we can reduce our fraction, and we can get that x is equal to 52 over 3. All right, moving on to the next one here. we have another opportunity to use the laws of logarithms and simplify the left-hand side so that it's one logarithm base 11 in terms of one argument. So what we have is logarithm base 11. Now we have that 5x plus 2. We're going to multiply that with the 3, and we're going to divide by the 4x. And that whole thing is going to equal 2. So, as it says here, do some work with the laws of logarithms. When we do that, we get log base 11 of this whole expression equaling 2. Now we can rearrange this. 11 to the exponent of 2 is equal to the argument. We've done that rearrangement many times now. Now 11 to the exponent 2 is equal to 121. So we're able to say 121 is equal to this expression. Let's multiply both sides by 4x, giving us 484x equaling 5x plus 2 times 3, which is the same as 15x plus 6. And from here, it's a pretty easy question to solve. We ultimately get x equaling 6 over 469. Now, how about if we have this question? This one's going to be pretty interesting here. We're going to see a little surprise at the end of this question, perhaps. What we do is we see that on the left-hand side, we're adding two logarithms. So we can make that one logarithm where we're multiplying the argument. So it's the log base 19 of x minus 3 times x plus 8. And that's going to equal the log base 19 of 12. Okay? So that's what we've got here. Now, since it's log base 19 on both sides, by observation, we can say x minus 3 times x plus 8 is equal to 12. Now, what we can do is, now it's just, as you might recognize, it's just a quadratic equation that you've done in earlier grades of math. Expanding the left-hand side, we're going to get x squared plus 5x minus 24 equaling 12. And then we're going to solve that out. Okay, so subtracting 12 from both sides, factoring both sides, we end up with x plus 9 equals 0 or x minus 4 equals 0. And so on first glance, a lot of people will say x can equal negative 9 or x can equal 4. But that's actually technically not true, because remember something that we said a long time ago that we haven't focused on a whole lot. We said that the argument of a logarithm must always be positive. And actually, so must the base as well, but we're not worried about that right now. So we're saying that this x minus 3 must be positive and x plus 8 must be positive. Well, if we let x equal negative 9, neither of those is positive. So this is what's called an extraneous root. But if we let x equal 4, they're both positive, and so it's all good. So here we go. This is the explanation. Remember that the argument of a logarithm must be positive. If x equals negative 9, then at least one of the arguments is negative, and in fact, both of them are negative. It's only required that one of them be negative in order for it to be extraneous. But in this case, both of them are negative, so that really makes the point. X equals negative 9 is extraneous. But x equals 4, that's legit, because when x equals 4, both of these arguments are positive. That's very valid, so that's our final answer, x equals 4. So let's look at restrictions. You should always check every possible answer against restrictions the way we just did here. Now, in math, not just in logs, but in math, the most common restrictions are, this one you know, the denominator of a fraction cannot equal 0. That's a common way to determine a restriction. Another one is that the argument of a square root, in other words, the part underneath the square root, has to be greater than or equal to 0. So if we do the square root of x minus 5, for instance, we know that the interior, x minus 5, must be greater than or equal to 0. And actually, technically, if you want, that actually applies for fourth roots and sixth roots anyway, any even root. That is another expression. Now, that's another restriction. Another one is that the argument of a logarithm must be positive. That's what we were doing in this question. So now we're introducing you to like a third type of restriction that comes up in math sometimes. And finally, another one that comes up in math sometimes is the base of a logarithm must be positive and cannot equal 1. That one doesn't really come up a lot. In this course, you're going to come up against this one a lot. The argument of a logarithm must be positive. Okay, so let's do some more questions. In this one, let's solve for x given that the log base a of x plus the log base a of 3x minus 2 is equal to 0. And when we write this on the end, don't sweat that so much. All we're really doing here is we're just saying to you, hey, this thing right here, it's a positive base and it doesn't equal 1. But you already knew that. But in a question, you'll often see that written just kind of like to be technically accurate. Question writers will write that a lot. Okay, nothing to worry about here though. So what we can do now is we can use our product law of logarithms, which states that if you're adding two logarithms, what you can do if they have the same base is just multiply the arguments and make it one big logarithm. Okay, so log base a of x plus log base a of 3x minus 2 is really just log base a of x times 3x minus 2, and that's equal to 0. Okay, now that we have this, we can convert it to the equivalent exponential equation, because this isn't a situation where we had a log on one side and a log on another. This is a situation where we had a log on one side and a number on the other. So what we do is we say the base of the exponent raised to 0 is equal to x times 3x minus 2. Now, since a is a non-zero number, we know that a to the 0 is equal to 1. No matter what non-zero value we put in for a to the 0 will always equal 1. Okay? So this is actually the expression we get. 1 is equal to x times 3x minus 2. Now we go back to a previous grade's math. That means 3x squared minus 2x equals 1. We make one side equal 0. We factor, and we solve. And what we end up with is x equaling negative a third, or x equaling 1. Okay, so on first glance, you might say we've got two answers. But if x equals negative a third, then this argument here is negative, and this argument here is negative. Neither of them can be negative, let alone both. So that's an extraneous root. So if you put x equals negative 1/3 in the answer box, you're losing a mark. But x equals 1, that's legit, because if x equals 1, then this argument is positive, and this argument is positive. And so this is a valid answer, x equals 1. All right, this is kind of an interesting one. What if the log base 6 of the log base 7 of x is equal to 0? All right, this is kind of interesting. What we do in a situation like this, what I say is let's let this inner piece right here, let's let that be a. So we're going to change this to the log base 6 of a equals 0. And then we're going to do a little solving. We're going to be able to say that 6 to the exponent 0 is equal to a. But we know that 6 to the exponent 0 is equal to 1. So we're going to be able to say 1 equals a. That means we're going to be able to restate this and say, since 1 is equal to a, we said a early on is equal to log base 7 of x. So basically what we're saying is 1 is equal to the log base 7 of x. And then rearranging this, we'll be able to say 7 to the exponent 1 is x. And x will ultimately, at the end of this question, be 7. And that's the reason why. Okay, so let's see if that didn't make sense. Typing it out makes a bit of sense. We're going to let a equal log base 7 of x. Remember that. So what we've really got is log base 6 of a equaling 0. Log base 6 of a equaling 0. Rearranging this logarithmic equation exponentially, we get 6 to the 0 equals a. 6 to the 0 is 1, so we see that a is 1. But remember what a is. A is log base 7 of x. So that means log base 7 of x is equal to 1, as we'll see on the next slide, and then from there we'll be able to solve it. Log base 7 of x equals 1, and once you see that, you can rearrange this. 7 to the exponent 1 equals x, so x ends up being 7. Okay? And in fact, if you try it, that actually makes sense. The log base 6 of log base 7 of 7, what does this equal? Well, the log base 7 of 7 is equal, the log base 7 of 7 is equal to 1 because 7 to the exponent 1 is equal to 7. So this is equal to 1. At this point, we're saying, what exponent would you put on 6 to give you an answer of 1? And the answer is 0. So if we let x equal 7, we get an answer of 0. So checking that answer, actually, we see that we're correct. Okay, now let's try this next one. We'll do the same sort of strategy. Let's let a equal the log base 4 of x. So that means we can rearrange this to say log base 5 of a equals 2. Well, therefore, that's like saying 5 to the 2 is equal to a, and we can say a is equal to 25. But we just said a is equal to log base 4 of x. So that means log base 4 of x is equal to 25. Well, what is it we're trying to solve? We're trying to solve for x. So rearranging this into its equivalent exponential form, we can say 4 to the 25 is equal to x. Okay? So let's show it to you typed. Same solution typed out. We let a be this interior quantity, and that means log base 5 of a equals 2. Rearranging this, we get 5 to the exponent 2 equals a, which means a is equal to 25. But remember what a was. A was log base 4 of x. So therefore, 25 is equal to log base 4 of x, meaning x is equal to 4 to the exponent 25. Well, 4 to the exponent 25, as we all know, is simply equal to 1,125,899,906,842,624. Obviously, we all knew that. And just joking. I promise you we won't have numbers that big on the test. But that's what x equals. Now, here's an interesting one. Let's solve for x in this situation. Okay, this is going to get pretty interesting here. What we're going to do, I'm just going to give you a little spoiler alert. We're going to re-express this. So this 1 in the numerator right here, I'm going to call that log base 2 of 2. And then in the denominator, I'm going to have log base 2 of 216. And this other one in the numerator, I'm going to call that log base 3 of 3. And I'm going to put that over log base 3 of 216. And so what I'm ultimately going to be able to do using change of base formulas, I'm going to be able to say that this piece is equal to the log base 216 of 2. And I'm going to be able to say that this piece, using change of base formulas, is log base 216 of 3. Now I'm going to see that I can use a product logarithm rule. So I'm going to have log base 216 of 2 times 3. In other words, log base 216 of 6. And then we'll evaluate that. The answer to that is 1/3. But let's sort of show a little bit more, let's sort of show with a little bit of verbs what's going on here. What we're going to try and do, as I've just shown, is make the numerator of each fraction a logarithm with the same base as the logarithm in that denominator. And once we do that, we can use our change of base formula. So for instance, in the first fraction, the denominator is a logarithm base 2. Let's make the numerator also a denominator with a base of 2. Okay, so to do that, what we're going to be doing is we're going to be saying log base 2 of some value a is equal to 1. And now we have to solve for a. Well, if 1 is equal to log base 2 of a, then obviously 2 to the exponent 1 is equal to a. And that's what we get here. 2 to the 1 is equal to a. Well, that would mean a is 2. So what we're able to do is say that first numerator, instead of calling it 1, we're going to call it log base 2 of 2, putting these two things together. And by a similar line of thinking, we're going to be able to say the other numerator is log base 3 of 3. And instead of 1s, that's what we'll have. Okay, now we've therefore changed it to x equals log base 2 of 2 over log base 2 is 216 plus log base 3 of 3 over log base 3 of 216. 1 is equal to this, and this one is equal to this. And like it says here, I really want to make this point. You don't have to show all the steps or all the explanation I just shown. If you understand how to do it, you can do it. And the reason we're doing it is focusing on this first fraction. We've got the same logarithm. We got the same base of logarithm in the numerator as in the denominator. Therefore, we can use our change of base formula, and we can say that this is the same as log base 216 of 2. And over here, we've got the same base of logarithm in the numerator and denominator. So we can say that the second fraction is log base 216 of 3. Just like that. Now we can use our product rule, and we can say that this is equal to the log base 216 of 2 times 3, which is 6. Now, let's think about what it is we're saying. We're saying x is equal to x is equal to log base 216 of 6. Well, that would mean that 216 to the exponent x is equal to 6. And from here, we can solve. We know the third root of 216 is equal to 3. So in other words, 216 to the exponent 1/3 is equal to 3. So therefore, x ends up equaling 1/3. So if x is equal to this expression, then that means that x is 1/3. And that's our final answer. And that's our last question in this video.